So, in the past couple of days, we've talked about one proportion tests. We talked about confidence intervals with a single proportion, and we've done hypothesis testing with a single proportion. So now we're going to look at, well, how do we do it with two proportions? Which is crazy, I know, but it's really not that crazy. I don't think it is. And you're probably freaking out. It's like, oh my gosh, like two proportions now? But it's not that bad. So our learning target is I can create a confidence interval for the difference between two proportions. So remember, a confidence interval is how we estimate a population parameter. How we take a sample and sort of guesstimate where our parameter could be, what how confident, and then how confident you are where it could be. So why do we have to deal with two proportions? Well, maybe a researcher wants to compare two different groups with each other. Like taking how this pill affects boys compared to how the pill affects girls, or what percentage of boys do their homework versus what percentage of girls do their homework. What percentage of people are employed in Knox County versus the percentage of people who are employed in Clay County, the percentage of people living on welfare in Barberville versus the percentage of people living on welfare in Corbin. And so we can take these two proportions and we can see if there's any difference between each other, see if there's if this is this, what's the likelihood of the other occurring. And we can use the difference between these two samples to understand the difference between the two populations. So if we looked at like 1,000 people in Corbin versus 1,000 people in Barberville, we can maybe extrapolate that to the whole city of Barberville versus the whole city of Corbin. So with new proportions, we got new formulas. So because our two samples are independent, we can just add their variances. So remember, when we add two samples together, we just add their means and we add their standard or we add their variances. And so we get the standard deviation of P1 minus P2 equals the square root of P hat 1 times Q hat 1, divided by N1 plus P2 hat times Q2 hat over N2. And so obviously P1, Q1, N1 refer to your first proportion, and P2, Q2, and N2 refer to your second proportion. So again, these formulas look really familiar because we have been using them for the past couple of weeks. And so basically our standard deviation is we're doing exactly what we've been doing, but instead of doing just P1 PQ over N, we're doing now P1 Q1 over N1 plus P2 Q2 over N2. And of course, we always need to check the assumptions. So, of course, there are three basic ones. The is it random? Is the sample size is both sample sizes less than 10% of the population, and for both samples is NP greater than or equal to 10, and is N times 1 minus P greater than or equal to 10. So we need to actually apply the 10% rule and the large counts rule to both samples, yes. But we also need to check if the two proportions are independent. Remember what independence is: the probability of me being selected here doesn't affect the probability of something else happening. So, but most of the time things are going to be independent. So, two proportion Z intervals. We can use confidence intervals to estimate the difference between two population proportions. So we have, let's say, we can find the difference between two sample proportions, just subtract them. But we don't exactly know what sample one's population proportion is and what sample two's population proportion is. So that's when we create the interval, and sort of use it to compare the two differences. This is a little bit different than what we've done before because well, the confidence interval we just looked at, oh, the true population. Where's the true population? Where's the true population of population 1? And where's the true population of population 2? So now we're looking at the differences of the true population. So the interval, we have p hat 1 minus p hat 2. Again, we're looking at the differences, so that's why it's p1 minus p2. Plus or minus the critical value. Again, same ones as last time. 95% confidence interval has a critical value of 1.96. Confidence interval of 0.9 has a critical value of 1.65, etc., etc. And your sampling error again is just your standard deviation. And we can just interpret it just the same as our last confidence interval. So, I am 95% confident that yada 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 yada. So, let's go through an example. How much difference is there in the proportion of male drivers who wear seatbelts when sitting next to a male passenger and the proportion of who wear a seatbelt when sitting next to a female passenger? Of 4,208 male drivers with female passengers, 2,777 or 66% were belted, but among the 2,763 male drivers with male passengers, only 1,363 or 49.3% wore seatbelts. Remember, the first thing we always do is we gotta check your assumptions. 1. Are the two groups independent? Yes, the proportion of men who wear seatbelts sitting next to a male passenger does not affect those that sit next to a female passenger. 2. Is it random? Yes, it said it was randomly sampled. Is the sample size less than 10% of the population? Yes. Clearly, there are more than 4,200 male drivers do not make up less than 10%, and 2,763 is definitely less than 10% of the population. And success failure, 2,777, they're all greater than 10, as you can see. Greater than equal to 10. I can't figure out how to put a greater than equal to sign on my slideshows, but for the most part, they are greater than equal to 10. So now we're going to construct the interval, and these are the two formulas we're going to use. So we have p hat 1 minus p hat 2 plus or minus the critical value times our standard error, which again in this case is your standard deviation. So the equation on the bottom is going to flow into our standard error. And so from there, we need to calculate our standard error, which is just we're going to plug in 0.66 times 0.34 divided by the number of male drivers, which is 42,800, plus 0.493 times 0.507 divided by 2,763, all square rooted. And that's how we get our standard, our sample, blah, 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 our standard error, which equals 0.012. Again, so now we're going to look at the difference of our two proportions, which is 0.660 minus 0.493 plus or minus 1.96 times our standard error, which we just found out was 0.012. 1.96 times 0.012 gives us 0.024, and 0.660 minus 0.493 gives us 0.167. And so from there, when we add and subtract it, we get 14.3% to 19.1%. So our interval is between 14.3% and 19.1%. So now we conclude, as always, I am 95% confident that the proportion of male drivers who wear seatbelts when driving next to a female passenger is between 14.3 and 19.1 percentage points higher than the proportion who wear seatbelt when driving next to a male passenger. Notice it says higher, so because it's positive, we can say 14.3 and 19.1%, and therefore it is higher. If it was negative, we would say lower. So if it was negative 14.3, negative 19.1, we would say lower than, but in this case, it is higher. Again, so it's very similar to what we've done before, but now instead of using a standard deviation for one proportion, now we're looking at the standard deviation of two proportions. So another example. Among randomly sampled teens aged 15 to 17, 57% of 248 boys had posted online profiles compared to 70% of 256 girls. Gross. How much difference is there in the proportion of boys who posted online profiles compared to girls who posted online profiles? So again, first thing we do, check the assumptions. Is it random? Yes. 248 boys and 256 girls are definitely less than 10% of the whole population of boys and girls. Are they independent groups? Yes. And success and failure. So you can calculate it, but it is pretty much big enough than that. So this is where I think the hardest part of these problems are constructing an interval. So why don't you go ahead and try it on your own, set up the equation yourself by following the first example, and then I'll finish up with this problem and you can check if your answers are right. But I'm just going to keep going on. So I mean, for the sake of learning, for the sake of doing well, and for the sake of having confidence in your own ability, I would suggest you do some of these problems before continuing on. So with that said, let's move on. So now we're going to construct that interval. So among randomly sampled teens aged 15 to 17, 57% of the 248 boys had posted online profiles. And so we have 57% pointing towards the P hat boys and Q hat boys divided by N boys. Instead of using 1 and 2, I'm using boys and girls just so we can differentiate them more easily. Yada yada yada. 70% of the 250 girls refer to that one. The P hat girls, Q hat girls divided by N girls. And so now let's just plug in the numbers we've got. So when we plug in the proportions of the boys and the girls, we end up with the square root of 0.0. The square root of 0.57 times 0.43 divided by 248 plus 0.70 times 0.30 divided by 256 equals 0.0425. Then we take the 0.425, we multiply it by 1.95, and that gives us 0.0829. And so we take that 0.0829 and we add and subtract it from the difference of 0.57 and 0.70, which gives us then our intervals of negative 0.047 and negative 0.213. And with that, we can conclude. We can be 95% confident that among teens aged 15 to 17, the proportion of boys who post online profiles is between 4.7 and 21.3 percentage points lower than the proportion of girls who do. It seems clear that teen boys are less likely to post profiles than girls the same age. Bada bing, bada boom. Come to class tomorrow prepared, and we will talk more about this. See you later.